So this is the pseudocode for finding the minimum spanning tree for the Prim's algorithm. This is structured pseudocode. It has a while loop, an end while, and actions to do inside that while loop. It does a few things. It initializes V to be the set of all vertices in the graph that it wants to find the minimum spanning tree for. It initializes an empty set, which is the tree it's going to create, the spanning tree it's going to create. And it initializes a variable called cost. So the way it's basically working, it's using these two sets, T, the set that it's got, that it's building up to create the minimum spanning tree, and what has not been, which nodes have not been included so far, which is all the graph nodes minus the ones that are already in the minimum spanning tree. So I wanted to do a trace of this particular algorithm so that you could understand it. And I'm going to run it on this particular graph right here. So you can see here. So this graph is a weighted graph, so all the edges have a cost associated with them. And that might be the cost to travel, say from A to D is 4 units, whatever that is. So we observe when the Prim's algorithm starts off, it has this initialization phase. It puts in into the set V, all the nodes that belong to graph G. So for this particular graph, that's going to initialize this set V to have A, B, C, D, E, F in it. And the number of nodes in this graph is equal to 6. It initializes T, the minimum spanning tree, to be an empty set to begin with. And it sets the cost value to be 0 to start with. You'll notice when it initializes T to be the empty set, at this point, the number of nodes, the nodes minus those in the tree, are exactly the same as the graph node because nothing's been included in the tree node graph. So then it picks a random, add any random vertex from the set of V to the set T. So just pick a random vertex, let's say it's D. Put it in the set T, so now T has one element in it, the node D. So the number of elements in T is equal to 1, and V minus T, that set, which is all the graph nodes minus the ones in the tree, is A, B, C, E, F. So we reduced that little set by one element because we've got D in the T set. So the number in the set V minus T is now 5. So this is important because this is what this while loop is checking to keep on doing the work. So while the size of T is less than the size of all the nodes in the graph, it's going to keep on doing work. So let's do a trace of that. So that while loop is doing most of the work there. So I need to just draw this out. It's not very easy, but let's try it out. So I'm going to set up what we said. We've got a graph that was, the tree graph was initially empty, and the set of nodes for this particular graph is A, B, C, D, E, and F. So we're going to pick a random node. Okay, let's do that. So we're going to pick a random node D. Okay, so looking at how that looks like, so what we've got here, we've got our graph T, and let's have a look at our graph V minus T. So if we pick a random node D and include it in the graph T, then what have we got not in T that belongs to the rest of the graph? We've got A, B, C, E, and F. And if we look at the cost of all those weighted edges, bear with me here, I'm just going to try and draw this on. So this one from D to A is 4 units, D to B is 3 units, D to C is 4 units again, D to E is 9, and D to F is 5. So inside the while loop, it says find the vertex which has got one end in T and the other end in V minus T with the smallest weighted edge. So you can see that that's going to be this one here, 3, D to B. So that is the one that's going to be selected. So cost, remember, was originally 0. So this one is going to be selected, and it's going to have its weight added to cost. So it's going to be 0 plus 3, which equals 3, and the edge selected here was D to B, which has a weight of 3. Okay, so now we've got 2 elements in the set T. We're going to have D and we're going to have B. They belong in the set T. So that's a little set there. This is what is in the set T so far. And this is what is not in the set T so far. That would be A, C, E, and F. So let's have a look at what edges we have that span these 2 sets. And we can examine their weights. So we've got D to A, which is 4 units. D to C, which was also 4 units. D to E, which was 9 units. D to F, which was 5 units. And now we have B in this set as well, the T set. So it has an edge that goes from B to A, which is 1 unit. And it also has an edge that goes from B to E, which is 8 units. So we've got D and we've got B. All right, let's have a look. Which one is the cheapest? Well, obviously this one from B to A is the cheapest one. So now cost is going to become 3 plus 1. And we are going to select the edge B to A to include in the spanning tree, which has a cost of 1. So let's keep going. I think I need to go to the next page for this one. I'm running out of room here. So I'll just take a screenshot of this one so I can keep going on to the next page. So that's what we're up to so far. So let's go to the next page and I'll paste that in. So we're on our way here. Let's see if I can do that. Hopefully I can. Oh no, can't seem to do that. Not able to do that. So here it is up there. Let's just look at it up there. So what have we got left? We're keeping track of T here and B minus T. We now have included in this set, we've got D, B, and A. And what is not in the minimum, which nodes are not in the minimum spanning tree so far? That's C, E, and F. So let's examine all those edges going across these 2 sets. So D has an edge to C, that's 4 units. It has an edge to node E, that's 9 units. It has an edge to node F, and that is 8 units. B, what's left for B? B has a edge to E, which is that one? That is 8 units. And A has an edge to C, which is 7 units. So we look here and we find the cheapest one. That happens to be that one over there that goes from D to C. So this is currently the cost here. The cost here is currently 4, and we're going to add 4 to that, which means the edge that we have added now is A to C, which has a cost of 4. So if we keep going now, so let's keep going. Hopefully I have enough room here to do this. So now, how is our spanning tree growing? We've got now inside T, we've got D, B, A, and C, and the nodes not in the tree graph yet are E and F. So if we examine these edges that go across here, we've got, well, D's got an edge to E and F. D to E is 9 units. D to F is 5 units. From B, we have an edge to E, which is 8 units. A does not have any edges to any of those nodes, and C has an edge to F, which is 9 units. So we're going to pick the cheapest one, which happens to be this one, from D to F. So that's going to be a cost of, that was equal to 8. 8 plus 5, that is now edge D to F, which is 5 units. And the cost now is equal to 13. Okay, so let's have a look now. We're getting more and more nodes into the tree, minimum spanning tree. So now we have, we've got D, B, A, C, and F in there. And what is left over, we've only got node E that has not been included in the minimum spanning tree. So let's have a look at the edges that we could use. We've got D to E, there's one edge that's worth 9 units. We've got B to E, there's another edge there that's worth 8 units. And we have got F to E, which is another edge that's worth 2 units. So obviously this one is the cheapest one. So this is going to be 13 plus 2, which gives us 15. So that's using edge F to E, which is 2 units. Okay, so now let's keep looking. We are nearly done here. We've nearly done the whole algorithm. So now we're coming to the end of the algorithm. What is left in T and V minus T at this point? So in T now we have D, B, A, C, F, and E. And in V minus T we have an empty set. So we have now got the while loop. Now the size of the tree is equal now to the size of the nodes in the whole graph. So this while loop, that condition is no longer true. So it will stop doing that while loop and it will return the cost. So the cost is over here. The cost was equal to 15. So it will return that cost. Okay. All right, so now I just wanted to do a bit of a proof. This is following the proof of this algorithm. Let's try doing a proof by mathematical induction. With that idea of building up, we're going to be building up 2 sets. We have a set T and we have a set V minus T. We watched that running before. And what we're basically doing is selecting the cheapest edges to grow the tree. Okay, so let's use that for our proof by induction. So for proof by induction, we need a base case. So the base case is that Prim's algorithm, I guess the proposition is that Prim's algorithm is going to be correct, but the base case is when we have one node. Okay, so when we have one node, well, what is this algorithm going to do with just one node? When we look at this algorithm, it's going to have the number of, say our graph, we're just building it up. The only node that we've examined is the very first one. If there was only one node in the graph, I guess it would be, the number of nodes would be equal to 1. But let's say the number of nodes in the graph is equal to k. We don't know how many there are. But at the beginning, we want to say that Prim's algorithm is going to do the best thing, is going to do the correct thing. So at the very first instance, what will it do? It correctly sets cost to be 0. It's going to randomly select the first node and put it into the set T, whatever that first node is. And while the size of T is less than the size of the set of nodes for the whole graph, which is really going to be really big, V to K maybe, it's going to find the vertex, it's going to find a vertex with the smallest weight that's going to connect the node that's in T to the rest of the graph. And it's going to add that end vertex to T. So say the edge was V1 to VI. So V1 to VI was the cheapest edge. It's going to correctly add V1 and VI into the set T, and it's going to add the weight of V1 to VI to the cost. So that's correct. Okay, so now we're going to assume that the Prim's algorithm will work correctly for K nodes that have been moved successfully into the minimum spanning tree. So we're going to assume that's correct for K nodes in T, in the set T, and of course in the set V minus T, that will now have the number of nodes minus K in it. Okay, so we're assuming that is all correct. So when we get to the K plus 1 node, when the K plus 1 node is inserted into T, what does it then do? Okay, so we've got our set T now has the number of nodes in that is equal to K, and that's all correct. And what we have in set V minus T is the number of nodes in the whole graph minus K. So what we're going to do is we're going to try and we're going to span. This algorithm says while the size of T is less than the size of the whole, all the nodes in the graph, it's going to look at, just like we did in the trace there, it's going to examine all the edges that go across these two distinct sets. And it's going to pick the one with the smallest weighted edge. So all of those edges will have a weight 1, weight 2, weight 3. It's going to select smallest from the pseudocode. It will select the smallest weight, say weight J, that will connect. So we say that's weight J here. So it's going to select the smallest one of those, and the edge that might be relevant for is some node in T. So it's VI will have an edge to VJ with a weight of J. And that's the smallest one. So it will correctly put that into T. So T, the set T, will now have the subscript J added to it, together with all the other vertices that it's got, whatever they are. And there will be now the number of nodes in that set T will be equal to K plus 1. That will be correctly added. And then the number of nodes remaining to be processed in V minus T will be equal to V minus K minus 1, which is correct. Okay, so this will now progressively keep on doing this. So we'll repeat while condition is true. It will continue to select, we'll select nodes until the number of nodes in T equals the number of nodes in the whole graph correctly. Okay, so that is a proof by induction. So this is the inductive step here. And you'll notice I've been using diagrams, which are very helpful. So that might need a few more words there to explain what was going on, but that's the general gist of how to do a proof by induction for the Prim's algorithm.